and skills you gain understanding this technology is directly applicable in your growth toward the semiconductor industry. When essentially the idea is that we still do layer by layer manufacturing of a more complex electronic system. Is there the materials are higher quality, production is finer, a higher resolution of the size of objects are much smaller, and of course the performance and complexity of devices are also higher. Whereas in flexible electronics, we can maybe, at least at the entry level, understand simple layered devices that compose 2 electrodes, a couple of active layers in between. We can appreciate the passive devices like the resistors, inductors, capacitors that can be turned to formidable sensors, or in some cases they can be also used as active elements of electronic systems. Now, my task in the second round today, morning before we break for Intel presentation, is what are these technologies? What kind of technologies we have available in our disposal to print and to manufacture electronics at large and low cost scale? So I'm going to basically look into the more manufacturing and technology side in this set of slides. Don't forget, again, what we print on, we haven't even discussed. Don't forget, we can print on polymers and plastics. Paper, not any plastic, not any paper. There's some requirements for the quality and surface finish. We can do it on textile. Very different forms of textile. Foils, metal foils, okay? Extremely thin, flexible glass even, okay? All these are possible in our, so I'm not even discussing what we are building on. My question in this, or this set of slides, is addressing what kind of techniques available to us to make this low-cost, large area and additive-friendly, eco-friendly, in that sense, technologies. The main difference or main insight that we need to gather as we understand this technology, we've done some semiconductor basic 101 training yesterday for fabrication. We talked how important is the accuracy and quality in many cases, but in that cases you start with a substrate, you deposit films that you, for instance, shape into a different conducting or insulating elements. Then you cover them with a photoresist before you do lithography, which is patterning through a light and a mask on that top layer that is given with orange color. And after you develop that pattern, you obtain the replica of the mask on that film that you want to shape, and then that you can use that mask film as an additional mask, hard mask, to etch, remove underlying elements. So the photoresist is used in this case, obviously, as a mask element. And eventually you end up with the green film that you deposited early on, shaped in the form of mask that you brought in. So this is highly accurate. You could do this, Intel and others are doing this at below 10 nanometer, we know. But we're not aiming that. Remember, flexible electronics is in microns, not in nanometers. That's typically an important distinction. But what we can do is, we get a substrate, we go straight down to the deposit where we want it in the pattern we want it in one shot. So we cut all the layers in between. Now, what happens is, educationally or STEM-wise or cost-wise, when you cut down the middle layers and show you could put that down on a substrate, material in a specific shape, it simplifies the electronic manufacturing. It is the context for undergraduates, even younger students who are interested in electronics and manufacturing can see the end product quicker, and they can do this in low-cost tools, even in the classroom settings. And I believe this is where we have a lot of flexibility and interest. Why I believe Flextronics and flexible electronics is a precursor to learning advanced electronics manufacturing. And we have a lot of tools, more than you possibly probably imagine initially. So printing technologies can be largely, brought as non-contact techniques, where you don't have contact with the substrate, versus contact printing. But whether it's contact or non-contact, everything can also be brought into a third roll-to-roll printing, where, as I mentioned, you create rolls and seamless integration of one roll from entering to manufacturing one end with different printing and surface treatment tools, one after another in a single succession. We could do both non-contact and contact printings and integrate them for manufacturing environment in the roll-to-roll printing context. But non-contact printings, you could do screen printing. I will bring a kit upstairs we will not do the screen printing. It's a well-known technique, and you probably have seen. I will spend that time more useful for other techniques in the afternoon, but I will bring a set we have upstairs. We could do inkjet printing, slot die printing. We'll mention it a little bit. It's basically a similar concept, except you use a rolling and a plate with a specific slot to provide the ink. And on the contact printing, we have a host of technologies, most of them developed in offset printing in the early days, gravure printing, flexography, micro-contact printing, nano-imprinting, dye transfer printing, not mentioning transfer printing, where you could take a circuit on a chip, cleave off the first 10 to 1 micron to 10 micron, and transfer the chip onto a surface. That's another way of getting actually silicon chips imprinted into flexible format. As you do, a grand question that I did not explain or emphasize so far, how do we print? Where's the ink coming from? What kind of inks we have, right? Because after all, we are not using standard inks. We are using conductive or non-conductive specialized inks. Now, those inks will have a lot of nanomaterials, functional materials. That's where the secret ingredients. So you will find in flexible electronics, the starting point is often a lot of startups from university research, because in universities we can take time to invent new inks. What is an ink? Think about it. As a solvent is providing the solution capability, but the secret ingredient is the functional, typically solids that are suspended in that fluid. And that fluid, that suspended fluid, could be dye, just giving the color in the case of traditional paper printing for reading purposes, but we replace them with active electronic content, either metal nanoparticles, or semiconductor particles, or insulating specialized films. So this is where the secret ingredient, this is flexible electronics firmly embedded to nanomaterial synthesis from that perspective of ink. Once you get the ink, it doesn't work. For instance, you can get copper particles, 10 to 100 nanometer copper particles. Put that in a solvent, try to print, it doesn't work. Because copper at that small dimension immediately oxidizes and it becomes useless for you. What you need to do is, you need to add additives and surfactants, cover the copper particles with basically around it, coated with a molecular protection layer from oxidizing, and you also add surfactants so that it floats, interacts with the solvent, and becomes suspends in the fluid. Now you have ink you could take to a conductive form. Now it's a conductive ink you put into inkjet or other jets that we create for printing, jetting systems, and then print. When the solvent evaporates, leaves behind that metallic elements. Now you need to typically do a heat process, quick heat process, or flash anneal that dries the ink and leaves a conducting film behind. So that's the ink part. But how do you apply the ink is where the printing technologies come. You could do screen printing. We have seen in the earlier videos, basically you have a screen with high resolution gaps in between, small holes. This is typically a silk, in the olden days it was a silk material, right? That's why it's called silk screen printing. But today's metal mesh, you could easily do 100 micron. The limit of screen printing is about 50 micron. You are pushing the limits. The problem is that you are using mechanical push, and the ink particles can be smaller, they can even get through, but the forming the good quality film becomes problematic. gravure printing, what you're doing is there are two rotating discs in contact. Bottom disc is scooping up ink in its surface because it has basically a pattern that you want to print, and that pattern has low and high points. The ink basically uses the surface tension to reside in the gaps, and as you pass the printing material and the impression cylinder pushes the materials against that bottom disc, and the ink is transferred to the material. And this is rotating and happening really fast, and you are only, so the ink is basically in a reservoir, you're only picking up ink just about enough, and the excess drops back in. In the flexographic printing, this is a little 1 degree more complex in the sense that you are doing this, except you have used a doctor plate, and then I think what flexographic does, basically it adds an additional cylinder that I think more controls the amount of ink and the accuracy better, and it is also basically you could bring multiple inks in this technique if necessary. And in the jet printing, which is the further to the right, you use the standard inkjet. What is it? You have a micro reservoir or chamber which includes the ink, and you have an orifice, a small opening tip, and you push the ink in micro droplets. The droplet volume, you're talking about pico to nanoliters, typically picoliters. In very high resolution ones, I will show you example. And typically, consumer printers are using more like nanoliters, okay? How do you push the ink from this little chamber is the question, and typically either you use thermal or piezoelectric efforts, and these are we're going to talk about. So basically, these are some of the printing techniques. How do we form the jets? Is inkjet the only method? The inkjet, as I mentioned, use typically a piezo drive, okay? So there's a membrane that moves under applied voltage because it's a piezoelectric material and pushes the ink out of the orifice. And we have an inkjet printer upstairs that is industrial inkjet printer for these purposes that can do. Our device is on the right. This is what we have. The Manix 2851. You are seeing that it is in action. While it's printing a picture, and this is flat bed. It's not, paper isn't rolling, it's flat bed and the surface is heated. So you could actually print and dry immediately. Now, there's a very promising aerosol printing technology. This is what I believe a lot of industry is using today, because inkjets ultimately can get clogged or have sometimes maintenance issue. In this case, in the aerosol printing, what you do is you create a solution containing the ink, comes through the center line of the nozzle, and you have two, around that center line, you have air flow or gas flow that is focusing that and pulling that fluid down to the surface, and then this distance between the tip of the nozzle and the surface could be as much as a couple of inches. So you use the aerodynamics and the mechanical flow design to focus that outcoming jet, literally focus on the surface. Because this is about an inch or about the surface, you could move the sample in 3 degrees of freedom. You could also take the nozzle, rotate it around 3 degrees of freedom. So you could actually print on a tennis ball, ping pong, or a cylinder, any curved surfaces with this technique. Whereas inkjet requires a little more. I mean, inkjet can also print on curved surfaces, but when you are printing on random surfaces, this jetting technique is very, very useful. You have other techniques, extrusion-based, where this is like the 3D printing, traditional now 3D printing, extruding and heating and melting and then solidifying back again. A filament, this can be done at fine features down to the 100, I think 30 micron. That is useful in some cases. But electrostatic printing, jetting with electrostatic pulses is very promising, and that can also go down to micron level. We will show later on an example. Our jet nozzle printing or extrusion printer is called something called sonoplot. Sonoplot is essentially considered like a fountain pen. You dip a glass capillary. Here's the glass capillary. You dip it into the solution. It uploads the ink. by surface tension and capillary action. You don't do anything to upload the ink. You can dip it into any reservoir, pick up the ink mechanically by pressure difference inside versus outside. And then it uses the electrostatic agitation coming from this electrostatic ceramic, piezoelectric ceramic, PZT array. And then it jets out from the tip of the glass purely by ultrasonic agitation. And we print down to 10 micron with that. The issue with that is glass needs to be well made, otherwise it can chip away in the long run. So you can print with a glass tip about 5 times or so before it gets worse. So there's some techniques to heat up the glass and make it more durable. So these are the 2 printers that we have. But of course, there are other techniques. Spin coating, high velocity rotation of a disc to spread the film widely across large surfaces. This is well done. You can basically, you're not doing selective printing, you're just spreading the entire film across there. Obviously inkjet is mentioned, but the inkjet has 2 methods, remember? The inkjet thermal, by heating the ink and essentially you're boiling off a droplet, pushing by pressure difference, or electrostatic membrane. We talked about flexographic and then the roll-to-roll printing, and we also talk about use of active jetting films. Printing materials, that's the question that now we need to also remember that we are not talking about only conductive inks. Conductive inks are what I think started flexible electronics. Now you could make conducting lines just by printing, but we also need insulating inks. Conductive inks, we need higher conductivity and low conductivity to make different types of resistors, for instance. And often lower conductivity or instead of metallic conductive inks, we have carbon-based, carbon nanotube or graphene-based solutions that can produce interesting options, low cost and different resistivity ranges available with them. And we have obviously semiconductive inks as well. You can actually bring metal oxides and some of the organic semiconductors also printed directly. What do we print on? Typically, Captain, a polyimide film, you see this amber film. It's very common. If you open your phone, most likely the antennas on that phone is printed on this amber colored flexible element. That's Captain is the commercial name. Actually, the material is polyimide, and it is a very rigid, a very high quality polymer film that can withstand upwards of 200 degrees in temperature. So it doesn't deform, so it's very durable, and then you could actually use them in some rough conditions. I don't think spin coating needs introduction because of the workshop we already covered, but the spin coating is very good when you are just making a thin film and just put enough, spread it out. The velocity is important. How far you go, how fast you come up to that velocity is important, as well as as you spin down. So you basically make sure that you have the good adhesion. The surface needs to be conditioned. The ink or the material you want to deposit should have wet the surface. So wettability and surface use of surfactants may be needed if you want to get a uniform film. Roll-to-roll, we saw the roll-to-roll systems, rolling discs, transferring ink to the pattern, and then many versions of that exist, but this is for industrial. Typically, most university labs will not have roll-to-roll because the capacity is so high, and these devices are a little sizable. There's tabletop versions. I've seen as small as maybe 5-6 feet systems, but even that system can produce hundreds of sensors in an hour. Typically in research, unless you do a specific research for that reason, you don't need it. Here's another short video. How are we doing with time? Let's check. On this roll-to-roll manufacturing. high speed by any imagination, but the circuit is a little more complex and not regular in this case. You could also see it's a glossy end. There's a passivating surface there, so it's not just paper or plastic. And it's just exemplary. The jets, inkjets, you could heat the ink. The problem with the heater, heat-mediated inkjet, you're heating the ink again and again, and it can cause chemical issues, oxidation, this sort of issue. So heat is not really preferred method. Most modern systems use piezoelectric heating, piezoelectric membrane, expanding in the volume that is limited, therefore pushing the ink out. And the size of the droplets is very important. If you can do picoliter, you can go down to a couple of microns. If you cannot do a picoliter, if you do more like 100 picoliter or nanoliter, you're talking about 10 to 30. The best sort of commercial devices, they tell about 30 micron is the limit, practical limit. The issue is basically as you bring the ink out, the droplet forms, and the droplet is a dynamic thing. It's kind of changing shape as it moves down in the milliseconds or microseconds it goes down. It essentially oscillating because of the pressure waves, and as it splashes on the surface, it broadens. So you're not getting an exact shape raining down and remaining as it is. There's a dynamic process. In fact, they do an interesting thing with the inkjet printers. You put one drop, simple droplet, it comes down, and you make a solvent that is super fast in evaporating. What it does, it evaporates to form what we call coffee ring effect. Coffee ring effect, when you put the coffee mug on your table, if there's some spillage, you get a circle, right? You could make one drop land down, evaporate so fast, the remaining inks will form a micron scale ring. So this has been used actually in creatively. So you could actually use, if you do the engineering of one single droplet, you could go down to micron type of rings and circular elements. Screen printing, I did mention there's a little bit of repetition in my slides because I joined two sets I use in different contexts. And here's the industrial screen. Of course, you don't do use of hands in the case of industrial, but industrial ones are fast and very accurate, and then they can exert more pressure, more even pressure is very important, and they can actually be very productive for large-scale manufacturing as well. I don't think there's sound in this one. Puts the material down. Make sure no creases. First pass, and then here's a star pattern form. Here's the second one. This is manual, of course. You could actually do this roll to roll. The roll can move on, comes down, swipes, move on, etc. So this is very, and the doctor blade will be, I mentioned the name doctor blade, will be rotating version of this, where the screen is static. In the doctor blade, the elements will be on the perimeter of the surface of the cylinder. As it rolls, it will push the ink down, and there's basically different variations of this. And at the exit, you can heat it up as the material comes down. Here it is already printed. Obviously, this is large, very large pattern, but you could go down to 100 micron. A lot of the batteries, a lot of those blood testing elements in the diabetic patients use for pricking their fingers for blood tests, those things are today printed in this fashion. Okay, in the interest of time, the last bit of the nozzle techniques. So you could do spray coating, the nozzles. We'll talk about that in the next slides in more detail because I will show you some amazing results, recent available systems. So here you're as good as your nozzle, the distance and how forcefully you are pushing the material, what technique you use. Because as it comes out of the nozzle, it can spray out. You may prefer that for large area coverage, or you may want to focus it using different techniques. An interesting technique that is coming from surface science is dip coating. what you could do is you could assemble nanoparticles or nano ink or a monolayer on the solvent. You could dip the element, pull it very regularly and steadily out, and what is assembling on the surface as nanofilm, like oil slick, for instance, right? It will transfer onto the material. So this can be actually used for large object dip coating, very fast and large area. Okay. So some interesting results in nozzle printing. Here's a 1 micron, or in fact 0.8 micron system. This is a Polish company that recently, XTPL. So some of the results they show. So what they do is they've taken a very traditional and simple approach to the extreme. They simply push a high density viscous ink through a nozzle, steel nozzle, ceramic, I think aluminum nozzle. They have different options by pure pressure. But they adjusted things so right, they are able to get this content. This paste is not even an ink. It's 70 or 75% solid. So it dries really fast, and if you can do this right, you can also extrude that into three-dimensional objects. So this thing is 300 nanometer height. The distance, it is 1 micron accurate tape with 0.7 micron gap. Over here, they have other examples. They can go across the ends of a vertical wall very easily because their head can rotate, I think, about 45 degrees. So you can go across the vertical walls of, so they are using this in chip packaging, for instance. They can go over multiple steps, and they can, as I told you, do rounding shapes very easily. This system looks like this. It's not massive, it's actually, and it is one of my target. I'm writing a couple of proposals on this. Hopefully, try to get this because you could do 1 micron printing all day if you want with this material. The second technique that is this is kind of finest approaches of from Japan. This system is called superfine inkjet. They use high pulses on a nozzle glass, metallic coated glass tip, just like our sonoplot. The difference is sonoplot doesn't use voltage to excite ultrasound. Sonic, they use a voltage pulse on a glass nozzle coated inside with a metal electrode, and they can spit picoliter size droplets, forming this extremely high resolution patterns, and they can also extrude by spitting and moving in the Z direction, devices as small as 1 micron. They, I think, advertise 0.8 micron accuracy. And the system looks like this, just like another inkjet tip. And one of the good things, despite their high resolution, these things are actually very affordable. I'm talking about $100,000 range for electronic manufacturing. That's a reasonable cost. Plus, their consumable cost isn't immense. They superfine inkjet needs a glass coated capillary, and they are low cost relatively speaking. And the other one, XTPL, doesn't really need to replace because it's either steel or aluminum tip that lasts quite a long time. Okay, and they are not difficult to find materials. So that's where I end. So basically, these are types of printing techniques. And as you can see, I have hardly spoke about electrical engineering in these printing techniques. There are mechanical, chemical engineering techniques that are widely available. And we're talking about things, printing things from inches to feet to the micron, a very wide range. And we can basically do this additive manufacturing at different scales, at different details, depending on all those applications I indicated in the morning. So the quality, the limit is what ink do you want to print. So you need to get reliable inks, inks that are low cost, obviously shouldn't cost a fortune. And this is one key parameter. If the inks are in low supply, they could be expensive because only one company is making, right? But if you go volume manufacturing, roll to roll, you're buying gallons of this material, okay, you're using, so it becomes really, really affordable. And the second thing is the substrates. Your substrates and your ink should be consistent. Like any other manufacturing, if your supplier is giving you inconsistent quality, questionable material, your performance of printing will also become limited. So I will stop here. I guess this is the time, but Any questions are welcome on this printing technologies. Yes?
Is the volume of the pipe limited by the nozzle or the surface touching material, or what limits that volume?
A lot of things. Number one, I think nozzle and nozzle dynamics play big important, whether you are pulsing, whether you're using air flow to focus material, and then the nozzle shape even the nozzle element, because the fluid to nozzle interactions are important, but also the distance and whether you're landing at certain velocity, you splash a lot. You can have the smallest droplet which splashes and makes a splatter, and then it then lose the quality of the, and also the distance. So that is why the nozzle printers, some of them say 30 micron, 50 micron limit in resolutions, and the last two devices, they are able to get to 1 micron. And now 1 micron is very interesting because with 1 micron you could do packaging in chip and other electronics, MEMS, optics, packaging. That's very important, so that's really applicable. The fact that they can also do vertical walls is quite impressive.
So just out of curiosity, if you can make the nozzle dimensions nanoscale, then is it just that surface tension can't push the fluid through?
Yes, that's the limit. Yeah, that's the limit. And two limits there. Surface tension is your enemy then, because you really have a lot of forces. Electrostatic binding forces of the fluid, a solid fluid interface is so immense, so you can't really push this in narrow, long endings of nozzles. The second issue is also nanoparticles that you use for ink. Typically, there is a paradox. You want tiniest particle if you can, let's say 5 nanometer, 10 nanometer, but they become more susceptible to environmental impact, oxidizing or others. When you dry them, the film that you form is low resistivity, high resistivity, lower conductivity than the bulk material. So conversely, you want to maybe make bigger chunks, 1 micron particles, but they can go through the nozzles now. The sweet spot is 50 nanometer to 100 nanometer, a lot of the inks manufactured, because they're just big enough particles. When you merge them, these nanoparticles, they will form a film about a couple of 100 nanometer, maybe 100 nanometer with some continuity. That's the kind of sweet spot. Therefore, the nozzle, you're right, we can't really do nozzle. If we could do it, literally we could print at 10 nanometer. That would be wonderful, but that's the limit. You're talking about enormous pressures. Yes?
I'm guessing there's, I'm sorry. I'm guessing there is limitations based upon the particular type of technology for the printing that you're going to do, based upon the substrate that you want to print on, and
Absolutely.
the top coat that you want to put over.
Absolutely. Surface plays that's the hidden. Surfaces, that's probably the last, how do you say, fine print I should mention. Surface is very important. How you finish that surface, the roughness of the surface, okay? Because that ink that came in, the droplet, if it doesn't want to stick to the surface isn't wettable, it's going to roll around and it's not going to be very good condition. Conversely, if your surface is extremely porous, the ink will wick through. It won't remain in the surface. So you will lose the ink. You could put buckets and it will just soak up. It goes everywhere inside that volume. So the surface finish, and that's one issue in paper. You can't print in every print because a lot of the paper will wick the solution. So you need most of the papers finished with a fine top layer, for instance, for good printing purposes. Exactly. So surface finish is very, very important. Also, velocity. If you're doing roll-to-roll printing, you're going so fast. You could smudge things, so you need to give enough time for dynamics of that droplet or printing element to dry or interact the right way. One last thing is you need to do a lot of quality control like any manufacturing. So in roll-to-roll systems, often there will be test stations about thickness monitoring, line sort of accuracy monitoring, etc. So those things will add up, obviously, to the complexity.
So in traditional integrated circuit semiconductor manufacturing, you're talking about layering. So
Yes.
there's a Z component here
Okay.
too. Is the same thing?
Same thing. We just
How about dissimilar materials overlapping?
exactly. We are more flexible with materials. We can so one roll or one printing station in the roll-to-roll does one layer, moves on to the next one, adds another layer. Next one adds a conductive layer or electrodes in right places. So we keep adding on. We are doing the same game in a simpler, much simpler and much higher, lower resolution. I saw a hand there, yes.
In case of changing the substance, that is
The
going
ink?
to be, yeah, the ink, is there any chance to change it? And if so, how you control the density of that? Because you said that this
Very good question. That's I didn't want to get too technical for general purpose. The viscosity of the ink very important. Inkjet is limited typically in the range of viscosities, not too low, not too high. Whereas some of the nozzle printers have a lot wider range. So the viscosity is a very key element. Changing ink is very secret kind of challenge here. In an inkjet, typically you have one ink, one cartridge. So you need multiple cartridges for multiple inks. If in a head put on the head with multiple drive electronics, so that can make more complex. But then you could do multiple. Our Sonopola printer, the one that looks like fountain pen, this is why we bought it. We can dip on any ink, write it, bring it to the solution to clean it, clean the tip, dip it into another one. So we could keep doing this as long as inks are easy to wash off. Typically, you need to use water or alcohol-based inks so that they are easy to wash off. That's a key thing. Yes. Otherwise, typically you don't want to really, in research, that's doable. In manufacturing, you want to dedicate one system for one ink and keep doing reliable the whole day. That's how they do it in the real manufacturing environment. All right, I think my time is up. Any other question? We can speak over the break and lunch.